Hi everyone, we are the students of BMSc College of Engineering, Bengaluru, presenting you the concept of Ofdm for 4G mobile communication under the guidance of Dr. K.R. Sudhindra sir. And these are our team members, Raghavendra, Bharath, Prashanth and Kiran Kumar. These are the contents. A number of technologies are being integrated by the telecommunication department as they are preparing for the next generation of mobile services. One of the key changes they have incorporated in the multiple access technique is that in earlier days they were using FDM for the mobile communication. Now they have incorporated OFDMA, which refers to the orthogonal frequency division multiple access, in which users are provided with the set of subcarriers overlapping in the frequency domain. However, the subcarriers are specially designed to be orthogonal to each other, which allows to occupy same bandwidth without any interference. And the main advantage is that the elimination of the guard band. As a result, subcarriers are being closely packed to each other, increasing the two periodic signals are orthogonal to each other when the integral multiple of the product for a one paired is equal to 0, which means that if two sinc functions are multiplied in frequency domain, which results in a 0. The main advantage of using OFDM is that conservation of bandwidth. As you can see, the lot of bandwidth is conserved by using OFDM rather than using FDM. These are the transmitter and receiver blocks of a basic OFDM system. We are making use of QPSK and QAM technology for modulating the data as well as for demodulation of the data. In 20 MHz of channel bandwidth, we are utilizing only 18 MHz as the rest of the 2 MHz is saved for guard band. The lowest subcarrier frequency is of 15 kHz. As the number of carrier increases, the bandwidth also increases. As you can see, the 20 MHz channel bandwidth, we have got 2 MHz guard band. We have got 1200 subcarriers, which is divided into 600 and 600. So each subcarrier is of 15 kHz. So 1200 into 15 kHz results in a 18 MHz. And 18 MHz plus 2 guard band, which is equal to the channel bandwidth 20 MHz. As you can see, this is the constellation diagram for the QPSK. For 2-bit QPSK, we'll be having 4 symbols, that is 2 power 2. For 4-bit QPSK, we'll be having 16 symbols, that is 4 power 2. And for 6-bit QPSK, we'll be having 6 power 2, 64 symbols. This is the comparison of frequency domain representation and time domain representation. For 15 kHz signal, we'll be having 1 cycle, and for 30 kHz signal, we'll be having 2 cycles. And the duration of the signals will remain same for all the signals, 6.6, that is 6.67 microsecond, as I said before, which is symbol duration, 1 by subcarrier frequency, which is equal to 1 by 15 kHz. As you can see, there are 1200 sync waves and subcarrier are overlapping in frequency domains. We can notice that we have 0 component at the peak of each subcarrier, which is known as orthogonality. The evolution of OFDM for 4G mobile communication will be continued by my friend Raghavendra.
Okay, myself Raghavendra, I'm gonna talk about the 4G communication. In telecommunication, 4G is the fourth generation of cellular wireless standards. It is a successor of the 3G and 2G families of standards. A 4G system is expected to provide a comprehensive and secure all IP-based mobile broadband solution to laptop, computer wireless modems, smartphones, and other mobile devices. It includes facilities such as ultra broadband internet access, IP telephony, gaming services, and streamed multimedia may be provided to the users. The 4G mobile communication systems provide a wide variety of services from high quality voice to high definition video to high data rate wireless channels. Now let's see how can you incorporate OFDM in 4G mobile communication. OFDM is a subset of FDM in which a single channel utilizes multiple subcarriers on adjacent frequencies. In addition, the subcarriers in an OFDM systems are overlapping to maximize spectral efficiency. Ordinarily, overlapping adjacent channels can interfere with one another. However, subcarriers in an OFDM systems are precisely orthogonal to one another. Thus, they are able to overlap without interfering. Two conditions must be considered. Each subcarrier has exactly an integer number of cycles in the FFT interval, the number of cycles between the adjacent subcarriers by exactly 1. In order to use multiple subcarriers to transmit an individual channel, an OFDM communication system must perform several steps as shown in the figure. In an OFDM system, each channel can be broken into various subcarriers. The use of subcarriers makes optimal use out of the frequency spectrum, but also requires additional processing by the transmitter and receiver. This additional processing is necessary to convert a serial bit stream into several parallel bit streams to be divided among the individual carriers. Once the bit stream has been divided among the individual subcarriers, each subcarrier is modulated as if it was an individual channel before all the channels are combined back together and transmitted as a whole. The receiver performs the reverse process to divide the incoming signal into appropriate subcarriers and then demodulating this individually before reconstructing the original bit stream. The next block is modulation. The modulation of data into a complex waveform occurs at the inverse fast Fourier transform stage of the transmitter. Here, the modulation scheme can be chosen completely independent of specific channel being used and can be chosen based on the channel requirements. In fact, it is possible for each individual subcarrier to use a different modulation scheme. The role of the IFFT is to modulate each subchannel onto an appropriate carrier. Now let's see how exactly it works. We have a long data string that has been generated. Each string is divided into 2 bits and given to the QPSK modulator. The modulation scheme we are using is QPSK, that is quadrature phase shift keying, where each symbol will be denoted by 4 different phases. As shown in the figure, we can see the different phases are 45 degree, 315 degree, 135 degree and 225 degree. Now coming to the channel bandwidth, we have chosen the channel to be of 20 megahertz, out of which the user gets 18 megahertz for the data. In this 18 megahertz, we'll subdivide the carrier into multiple subcarriers of 15 kilohertz. So we place the subcarriers in 15 kilohertz, 30 kilohertz, 45 kilohertz and so on in the positive frequency. Similarly, towards the negative frequencies, we have from minus 15 kilohertz, minus 30 kilohertz, minus 45 kilohertz and so on. Then each subcarrier, if you divide it by 1 second, you will get about 66.7 microseconds. This becomes one slot. So that in this one slot, you can either transmit it as 1 or you can either transmit it as 0. And this in generally it is called as a resource element. Therefore, in our OFDMA communication, one slot or one resource element is of 66.7 microseconds. So once the wave is QPSK modulated, these signals are then multiplied by subcarriers and placed in the channel. You can see the strings of zeros and ones. So totally it generates 1200 symbols that is transmitted from the channel. To achieve this, we require 1200 oscillators at the transmitter side, and if you want to receive the signal by coherent detection, again you require 1200 oscillators which generate 1200 different subcarrier frequencies for different symbols. Now the complexity is in the hardware. If the number of oscillators increases, the power requirement will be more. As the result, the practical implementations of OFDMA is not possible. So, in order to meet the practical considerations with the advancement in the digital signal processing, we use one more block, that is IFFT, inverse Fourier transfer. What exactly we do is the signals that are generated from the QPSK modulator are first sampled using your IFFT algorithm. Now we get a sampled version of all the signals and generate one composite waveform which can be represented by series of different symbols. So for this IFFT sampling, we require a sampling rate. The sampling rate should be always greater than the Nyquist rate, that is 2 times Fmax. As I already mentioned, the maximum allowable frequency for a channel is 18 megahertz. This 18 megahertz is again divided from plus 9 megahertz to minus 9 megahertz. Therefore, the highest frequency component is 9 megahertz into 2 will gives you 18 mega samples per second. So this 18 mega samples per second into 66.7 microseconds will almost give you 1200 samples, where 66.7 microsecond is one resource element, which is the unit of your OFDMA communication. Looking onto the table, you can see the comparison between the transmission bandwidth, sampling frequency and FFT size. If you choose your bandwidth of the channel of 20 megahertz, then the highest sampling frequency will be about 30.72 megahertz and generating the IFFT symbols of 2048. Now let's move on to something called as cyclic prefix. In wireless communication systems are susceptible to multipath channel reflections. A cyclic prefix is added to reduce ISI, that is inter-symbol interference. A cyclic prefix is a reception of the first section of a symbol that is appended to the end of the symbol. In addition, it is important because it enables multipath representation of the original signal to fade so that they do not interfere with the subsequent symbol. This figure shows how cyclic prefix can be inserted. If you consider your FDM technique, in FDM between the two symbols of subcarrier we insert one period called as guard period. But when this guard period is converted to a frequency domain, it causes some sync pulses to overlap. Therefore, in OFDMA technique, we insert something called as cyclic prefix between the two symbols. The cyclic prefix is nothing but a end portion of the next symbol is added as beginning of the first symbol. Therefore, when it is converted to a frequency domain, you can see in the second figure there is no interference between the symbols. Now, to choose the cyclic prefix duration, there is a calculation. If you consider your normal cyclic prefix and the frame size is of 15 kilohertz, that is the frequency of each subcarrier is 15 kilohertz, and your sampling period of 160, then you'll end up getting cyclic prefix length of 5.21 microseconds. And you can see the different calculations for different sampling period. So basically your cyclic prefix length varies between the sampling interval. Therefore, once the signals are passed through your IFFT block, you will get the sampled version of the composite waveform. To this sampled version of the composite waveform, we include cyclic prefix. That is, the end portion of the last symbol is added at the beginning of the samples. Then this composite waveform is passed through DAC, that is digital to analog converter, to get the analog signal. This analog signal is a composite baseband signal of your desired frequency 18 megahertz is passed through the RF modulator. Here we use RF frequency of 2.3 gigahertz. This 2.3 gigahertz has to be licensed by particular network provider. Therefore, it provides a band of 2320 megahertz to 2340 megahertz. You can see how the 18 megahertz signal is placed in your channel.
Well,
The so far discussed is the downlink process, that is from the transmitting antenna to the mobile device, how the communication takes place in your 4G LTE. Now let us see how does the uplink process happens in your 4G LTE will be discussed by the next person.
hello everyone, this is Prashanth. Even though there are many advantages of OFDMA, the IFFT summation of multiple parallel frequency domain signals which are used in downlink explained earlier results in high peak to average power ratio, which in turn results in high power consumption for signal generation. But handheld devices like mobile phones have limited power supply. Therefore, OFDMA can't be used in uplink. To overcome this problem, the LTE uses a technique called single carrier FDMA in uplink direction. In OFDMA, we have one-to-one mapping between symbol to subcarriers, but sc-fdma allows a symbol to be transmitted in parts over multiple subcarriers. For example, in OFDMA, one symbol occupies one subcarrier of 15 kHz, but in sc-fdma, same symbol can be distributed among multiple carriers of 15 kHz. In short, sc-fdma is the single carrier system with short symbol duration compared to FDMA. To achieve this, sc-fdma introduces a endpoint FFT block right after the serial to parallel converter in the OFDMA structure. The FFT block converts parallel sequence of symbols in time domain to different frequency points. Now, the peak to average power ratio is proportional to the square of the numbers involved. This causes sc-fdma to reduce peak to average power ratio by reducing the number of carriers.
Myself Kiran BR. This table shows the downlink OFDMA modulation parameters. In this table, the frame duration, subframe duration, subcarrier spacing is constant for all the frequencies. Frame duration is 10 millisecond, subframe duration is 1 millisecond, subcarrier spacing is 15 kilohertz for every frequencies. For example, consider if the channel bandwidth is 15 megahertz, then the frame duration, subframe duration, subcarrier spacing is constant. Sampling frequency is 23.4 megahertz, FFT size is 1536 and occupied subcarriers is 901, got subcarriers is 635, number of resource blocks are 75, occupied channel bandwidth is 13.515 megahertz and so on. This figure shows the LTE generic frame structure. OFDMA is an excellent choice of multiplexing scheme for LTE downlink. Although it involves added complexity in terms of resource scheduling, it is vastly superior to packet-oriented approaches in terms of efficiency and latency. In OFDM, users are allocated a specific number of subscribers for a predetermined amount of time. These are referred to as physical resource blocks in the LTE specification, the PRBs that have both a time and frequency dimensions. In order to know the OFDMA within the context of the LTE, we must study the physical layer generic frame structure. The generic frame structure is used with FFD. FFD means frequency division duplexing. Alternative frame structures are defined for the use with TDD. TDD means time division duplexing. However, TDD is behind the scope of our alternative frame structures are not therefore considered. In the figure, LTE frames are 10 millisecond in duration. They are divided into 10 subframes, each subframe being 1 millisecond long. Each subframe is further divided into two slots. Each slot is 0.5 millisecond duration. Slots consist of either 6 or 7 OFDM symbols. The OFDMA has various advantages like multi-user diversity means broadband signals experience frequency selective fading. OFDMA allows different users to transmit over different portion of the broadband spectrum. Different user perceives different channel qualities. A deep faded channel for one user may still be favorable to others. The third graph shows the multi-user diversity principle. This graph shows the efficient use of spectrum by using Ofdm. Receive simplicity means we can eliminate the intra-cell interference, avoiding CDMA type of multi-user detection. Orthogonality of code destroyed by selective fading. Only FFT processor is required. Bit error rate performance is better only in fading environment. Disadvantages of OFDMA. By using OFDMA, peak average power ratio is introduced. Peak average ratio power means it is the ratio of peak sampling value to the average sampling value, which is given by peak to average power ratio is given by x of t whole square divided by peak. Large amplitude variation increase in-band noise and increase the bit error ratio when the signal has 2 watt through amplifier nonlinearities. Synchronization. Tight synchronization between users are required for FFT in receiver. Paired signals are used for synchronization. Co-channel interference. Dealing with these is more complex in OFDMA than in the CDMA. Dynamic channel allocation with advanced coordination among adjacent base stations. Comparison. This table shows the comparison of various multiple axis techniques, and here the OFDMA has more features than any other multiple axis technique. The above table shows the OFDMA surpasses all the other schemes in terms of various parameters, so that we can conclude that it is a right choice of multiple channel access schemes for 4G mobile wireless networks. However, in spite of all the utilities of OFDMA, there are certain obstacles in using OFDM in transmission system contrast to its advantages. The LTE physical layer implementation a number of technologies to deliver on required for high data rates and spectral efficiency. OFDMA allows the downlink to provide a high as 100 Mbps in downlink throughput, while sc-fdma on the uplink reduce the design complexity for the user terminal by reducing PA/PR. Thank you.